In an unprecedented twist to our understanding of planetary science, the James Webb Space Telescope, JWST, has found strong evidence for an atmosphere on TOI 561b, a planet so fiery that its very existence challenges the basic principles of atmospheric survival under extreme conditions. As JWST directed its gaze toward TOI 561b, a revelation unfolded that perplexed astronomers around the globe. Nestled in the constellation of sextans, approximately 280 light-years from Earth, TOI 561b is a world so extreme that its very existence is a testament to the universe's capacity to surprise us. This exoplanet, categorized as an ultra-hot super-Earth, orbits its host star at a blisteringly close distance, completing a full orbit in just under 11 hours. The proximity to its star subjects, TOI 561b, to intense irradiation, heating its surface to a molten state with estimated temperatures soaring above 2,000 degrees Celsius. Traditionally, planets like TOI 561b were not expected to retain any significant atmosphere. The prevailing theories in exoplanet research suggest that at such close distances and extreme temperatures, any atmospheric gases should be stripped away by stellar winds and radiation, or lost to space through hydrodynamic escape. The atmosphere, if it ever existed, would have been thought to dissipate quickly, leaving behind a bare, inhospitable rock. Yet JWST's dayside emission measurements indicate a cooler than expected surface for an airless rock, consistent with a substantial atmosphere that redistributes heat, throwing a wrench into prior assumptions and suggesting that other forces or mechanisms might be at play in protecting or replenishing TOI 561b's atmospheric layer. The capabilities of JWST in studying exoplanets are unprecedented, particularly through secondary eclipse observations with its NIR SPEC instrument in the 3 to 5 micron range. By capturing the planet's thermal glow when it slips behind the star, JWST can infer the dayside temperature and test whether heat is being moved around by an atmosphere. This has allowed scientists to argue, with the strongest evidence so far for a planet like this, that TOI 561b's dayside is too cool to be a bare rock, pointing to atmospheric heat transport and a volatile rich envelope. Researchers involved in the work emphasize that this finding challenges current models of rocky planets under extreme irradiation and suggests we might be missing key physics of atmospheric survival. Rather than definitive composition, the result is a robust thermal inference. The most straightforward explanation is an atmosphere capable of moving heat off the scorching dayside. Following these observations, the astronomical community has been abuzz with hypotheses attempting to explain how TOI 561ba could maintain such an atmosphere. Some suggest the presence of a magnetic field that helps shield it from stellar winds. Others hypothesize about the atmospheric composition itself, potentially dominated by heavy molecules less susceptible to escape under extreme conditions. Another leading idea is continuous replenishment from a global magma ocean. Volcanic outgassing and rock vapor cycles could feed the atmosphere even as stellar radiation strips it away. Each theory opens new lines of inquiry and potential research, making TOI 561b a focal point for future observing campaigns. This unexpected result not only challenges prior notions about planetary atmospheres, but also enriches our understanding of planetology. As we continue to decipher the secrets of TOI 561b, we inch closer to understanding the complex dynamics of exoplanets, insights that could shape how we identify potentially stable worlds in the harshest corners of the galaxy. The puzzle presented by the stubborn air of a lava world serves as a vivid reminder of the surprises still lying in wait as we explore the cosmos. In a groundbreaking analysis, JWST turned its attention to secondary eclipses of TOI 561b, an ultra-short period world in sextans roughly 280 light-years away. The NIR SPEC data revealed dayside emission temperatures lower than expected for a bare rock, implying that a thicker atmosphere may be redistributing heat from the dayside to the night side. This finding defies long-standing models which assert that any atmosphere this close to a star should be quickly eroded by intense radiation. The scientific community was astonished. TOI 561b, being a lava world, should theoretically possess conditions too harsh to retain an atmosphere. The planet orbits its star in about 10.5 to 10.7 hours, with dayside temperatures likely exceeding 2,000 degrees Celsius, regimes under which an atmosphere should not survive for long. Yet the temperature inferences from JWST are most consistent with an atmospheric layer that modifies the planet's thermal properties. The research team notes that a volatile-bearing atmosphere, perhaps continually outgassed from a magma ocean, could explain the data and force a re-evaluation of atmospheric escape under extreme conditions. This perplexing discovery naturally prompts comparisons with other lava worlds, such as K2, 1, 4, 1b, and Kepler 10b. While these planets are similarly extreme, the evidence for atmospheres on them is not yet confirmed by JWST. Instead, they remain prime targets for upcoming observations to test whether heat redistribution and atmospheric signatures appear in their thermal phase behavior. If multiple ultra-short-period rocky planets show consistent signs of atmospheric retention or replenishment, that pattern could catalyze a significant revision in our understanding of atmospheric survival. The debate now focuses on the mechanisms that could allow such atmospheres to persist. Some scientists propose that planetary magnetic fields could provide partial shielding from stellar winds, helping slow atmospheric loss. Others emphasize the composition of the atmosphere, possibly rich in heavier species like metal oxides and silicates that are more resistant to escape. There's also increasing interest in atmospheric recycling, where volcanic outgassing and surface-atmosphere interactions continuously replace lost gases. If confirmed, these processes could broaden our expectations for which rocky planets can hang on to atmospheres. These findings challenge not only our understanding of planetary science, but also the criteria we use when thinking about life-supporting conditions across the universe. The existence of a heat-moderating atmosphere on such a fiery world doesn't imply habitability, but it does expand the range of physical environments in which atmospheres can survive. That broader picture matters. Atmospheres influence climate, surface chemistry, and long-term stability, key ingredients for assessing planetary potential, even in places far outside traditional habitable zones. Looking forward, the community is mobilizing to deepen these tests. JWST's continued observations, spanning secondary eclipses and, where possible, full or partial thermal phase curves, will probe additional lava worlds and constrain the presence or absence of atmospheric heat redistribution. Ground-based and space-based follow-ups will aim to tease out spectral features that hint at composition, while advanced models will simulate escape, outgassing, and magnetic shielding under extreme irradiation. Together, these efforts will show whether TOI 561b is an outlier or the first member of a broader class of atmospherically active molten planets. This revelation not only expands our horizons, but compels us to rethink our place in the universe. The result from JWST is a testament to human curiosity and the relentless pursuit of knowledge. It beckons us to look beyond conventional wisdom and to consider the myriad possibilities that the cosmos may hold. As we continue to probe the depths of space, each finding adds a new piece to the puzzle of planetary origins and the potential for diverse atmospheric chemistries beyond Earth, reshaping our understanding with every new discovery. This is not just science. It's an ongoing narrative of exploration and wonder, reminding us that the universe is far more intricate and surprising than we imagined. From the scorching surface of TOI 561b, JWST has gifted us a profound lesson. The cosmos harbors more secrets than our current science can grasp, and each discovery propels us further into the unknown, continually reshaping our quest to understand the universe and the potential for life within it. If you enjoyed this story, hit subscribe for more fascinating space deep dives every week. Thanks for watching.